All right, everyone, we will go ahead and get started. So welcome to this month's PCAST talk. Before we get started with our speaker, just a few announcements from the project. The first one that hopefully you've seen if you're subscribed to our newsletter is that we're very excited that last month we successfully submitted the concept study report for PRIMA. So our PI is extremely excited. It's been a huge effort by all of the folks involved. We're very grateful to everyone for doing everything from showing up to these talks to talking about PRIMA with your colleagues, writing papers, participating in the General Observer books, right? All of this helped us to get to where we are. The next step that we're waiting for is the site visit, which will happen in spring, in May, when the committee will visit and meet with the folks in Pasadena at the JPL site to ask more questions and get more information about the project. And then we're anticipating that the final probe selection will occur in late 2026. So you can find this information and again, more news from the project, including adding several more COIs from our various partner institutions. You can find all of this in the newsletter. Please look for it on our website. As well, you can find out information on how to sign up if you're not receiving that. So we have a number of upcoming talks, so we're going to be continuing to do this throughout the year. Right now we're finalizing sort of the next set after March, but in March we have another talk from Rebecca Levy at Space Telescope, and she'll be telling us about nearby galaxies and work that you can do on those structures with PRIMA. Some of our upcoming talks are also going to be talking about some of the general investigator science, so the surveys that PRIMA will be completing and how the community will be able to access data from that and the science that will be done with those surveys. So please look forward to those talks happening in the next few months. Today, of course, we're here to hear from Susan. So Susan will be telling us about magnetic fields with PRIMA and sort of a really unique capability is the polarimetric capability with PRIMA. So we're really excited to hear more about the state of the art with this and what the future looks like with PRIMA.
Okay. Thank you so much for having me here today to talk about magnetic fields in the interstellar medium. I've titled this Toward the PRIMA Era with the thought that I can't possibly do justice to everything going on in the study of magnetic fields in the ISM, but I would try and sort of pick and choose a few things from the recent past, from current work we're doing in my group, and from looking toward the future that really sort of set the stage or might spark useful discussion for the sorts of things that we are excited to do with Primager in particular, with a far infrared imaging polarimeter on board PRIMA. So I should say at the outset that any work I talk about that comes from my own group is in many cases the work of fantastic students and postdocs. Grad students are highlighted in the teal here, and you'll see their faces come up as appropriate. Caitlin Kropovich in particular, I believe is on the call right now, and is a great person to chat with about much of what I will say today. This is just to show you a sort of family portrait of some nearby galaxies that are observed in far infrared polarization. And so you can see that many of these images are, beautiful multicolor images of Hubble or Spitzer data, but overlaid on top of them are these swirls that indicate the measurement that we can infer from far infrared polarization, which is the plane of sky magnetic field orientation. Now these are nearby galaxies. These are from the SALSA survey led by Enrique Lopez Rodriguez. Nearby galaxy magnetic fields is its own rich science topic that PRIMA would really revolutionize, and so that should be its own entire talk. I just want to make the point that today we're going to talk about the magnetic fields that pervade the space between stars in galaxies, the magnetic field of the interstellar medium, with a focus really on our home galaxy, the Milky Way. And the existence of the interstellar magnetic field provokes all nature of very important scientific questions that are really just wide open territory. So we know that the magnetic field plays some still very poorly understood role in the coalescence of material like molecular clouds within galaxies, in the formation of interstellar structures, and eventually the formation of stars. That area in particular is one where you can formulate lots of specific questions where far infrared polarimetry could make a huge difference to our understanding. And so we'll focus on that a bit. But broadly, the interstellar magnetic field affects really every phenomena that we care about in understanding the evolution of our galaxy. So the character of turbulence in the interstellar medium is fundamentally magnetic and inseparable from the existence of the magnetic field. The structure of the magnetic field, of course, is very tied to the propagation of cosmic rays, and that affects the energy balance in our galaxy. And so the strength and structure of the galactic magnetic field in particular regions and as a whole is really something that we need to understand better as a starting point to understanding many of these open problems. And in the field of studying magnetic fields in the interstellar medium, we have a number of different tools in our tool belt. So we can measure, for example, Faraday rotation, typically at radio wavelengths, where we can measure the change in the linear polarization angle of light as it traverses the magnetoionic medium in our galaxy. We can measure synchrotron radiation from charged particles accelerated in the galactic magnetic field. And then we can measure two imprints of the interstellar magnetic field that are made visible to us by the presence of interstellar dust. And so in my little cartoon here, these gray ovals represent interstellar dust grains, which are on average not perfectly spherical entities, and which find a preferred alignment between their short axis, their spin axis, and the ambient magnetic field that they're sitting in. And so this has two consequences. One is that if you have intrinsically unpolarized background starlight that you observe in the optical or the near infrared, the selective absorption of these interstellar dust grains will imprint a partial linear polarization signal on that light. And that imprinted polarization signal gives you a measure of the orientation of the interstellar magnetic field in that dust between you and that star. And then, most directly relevant to PRIMA, those dust grains are also emitting thermal radiation, which we can measure most spectacularly at far infrared wavelengths as partially polarized thermal emission from these dust grains. And so the sort of tricky bit comes when we approach any particular problem in the understanding of interstellar magnetism, partially from the fact that each of these different tracers is giving us partial information. So in general, each of these tracers gives us access to one component of the interstellar magnetic field, either the component that is in the plane of sky or along the line of sight. And in general, these each probe a distinct phase of the multi-phase interstellar medium. And so, part of the challenge is, how do we combine data? How do we put the pieces together and understand the problems we want to understand? Now, I would be remiss if I stopped there for sort of listing our tracers. These are the main ones that I can. Okay, those are the tracers where I can make a nice, all sky map. But the most direct tracer of the magnetic field strength in the neutral ISM, neutral molecular ISM, comes to us from Zeeman splitting. And so my grad student, Marta Nowacka, is doing some good work to increase the number of Zeeman splitting measurements that we have to play with. Okay, so today I want to talk about some of sort of where we are, where we've been, where we're going. And where we have been for some years now in the study of galactic polarized dust emission. is really benefiting from this all sky map, 850 microns, 350 gigahertz, made by the Planck satellite. And so you can see again, this is the visualization of the measurement that we make from polarization of light at these frequencies or into the far infrared. The brush strokes here are a visualization of the plane of sky component of the magnetic field orientation that is measured in the dust, of course, integrated along the line of sight. And so that measurement, that inference that we make is really just the linear polarization angle that we measure of the light rotated by 90 degrees. That's the relationship between the plane of sky magnetic field and the polarization angle that we measure. And this incredible all sky map really enabled a good number of statistical studies of the structure of the magnetic field and filamentary structures in the interstellar medium. The Planck team themselves did a lot of great work analyzing the relationship between the magnetic field orientation and the orientation of structures in molecular clouds and in sort of ISM filaments in general. They identified this trend as a function of column density for filamentary dust structures to be more parallel to the projected magnetic field at low column density, moving toward or becoming anti-parallel, or oriented orthogonally to the local magnetic field that they sit in, toward high column densities. So this is great for sort of large area statistical studies. This had a big effect on my own work, my own thinking about the ISM. One of the fun, really unexpected discoveries that we made with these data is that in neutral hydrogen emission, so a tracer of filamentary cold neutral gas is very tightly coupled to the plane of sky, to the magnetic field that you measure as this plane of sky magnetic field orientation with a tracer like Planck. And so in this image, the brushstrokes in the top panel are showing you a measure of the local orientation of linear structures in neutral hydrogen emission. The bottom is showing you what we infer from the Planck data, the plane of sky orientation of the magnetic field. And in both of these panels, the little white sprinkles are this measurement that we make from optical starlight polarization. So that is also a tracer of the plane of sky magnetic field now between us and the star. The beauty of these Planck data really involved the fact that they were all sky and that we could probe sort of many different environments, at least at low angular resolution. And so we also learned a lot about the geometry, the effect of the geometry of the magnetic field on the statistical properties of the polarization data. So for example, here is an analysis of something that we call the polarization angle dispersion or polarization angle dispersion function, just a local dispersion of this plane of sky polarization angle that we measure with polarized dust emission, compared to the polarization fraction, just the measure of the fractional linear polarization of light at these frequencies. And so you can imagine that as your, if you have a sort of tangled magnetic field geometry, either within your beam or along the line of sight in your data, that can translate to affecting both of these tracers. That can translate to an increased dispersion of the plane of sky polarization angle and a decrease in the polarization fraction. And so to the extent that these two measurements sort of compensate one another, you're learning about the effect of the geometry of the magnetic field on both of these tracers. And that's important because we often want to separate that from other things that might affect one of these independently, and in particular, say, properties of your dust grains that might affect the polarization fraction. Okay, but this whole story is really best understood in the context of large angular scales and the relatively diffuse ISM. Actually, I'll say one more thing about that, which is that this correspondence between the magnetic field geometry and these measurements is really so predictive of some of the properties here at large angular scales that we can mock up the Q and U components of our linear polarization, or other ways of the polarization angle or polarization fraction, purely from the geometry of this neutral hydrogen emission, linear structures and neutral hydrogen emission. And so that's really its own whole story, but that's something that Brandon Hensley and I investigated that gives us another way to investigate the influence of the geometry of the magnetic field on these tracers. And this story is really one where we're benefiting in our inference about the magnetic field structure from the fact that our data contain a lot of information in the sort of morphology of the measurements that we're able to make. And so one of the benefits of imaging in general is that we can make resolved maps of structure that encode so much physics if we can just sort of figure out how to translate the physics questions we want to ask to the space of the morphological data, the morphological information that we have imprinted in our data. And so this, I think, it's been a fruitful line of inquiry in the recent past, and I expect this to be a way of organizing or asking some questions of the data where PRIMA will really shine. And that's because PRIMA would really be a massive step forward in our ability to map and understand magnetic fields on the scales of entire molecular clouds. So a few places in this talk, I have borrowed some Snapchats or some snaps, screenshots from the PRIMA General Observer Science book. This in particular is from the chapter led by Paddle et al., illustrating that while Planck made this, these all sky maps of the polarized dust information, really the native resolution of Planck at 303 gigahertz was about 5 arc minutes, and then for sensitivity reasons, really the study of molecular clouds with Planck data is limited to typically 10 arc minute or even coarser angular scales. And so that's very limiting when what you want is to understand the detailed structure of the magnetic field within molecular clouds and its relationship to this morphology, its relationship to the structure of dust and gas that we can measure or have even already measured with ancillary data toward a number of molecular clouds in our galaxy. And so the real promise of PRIMA is illustrated here as being, this sort of polarimetric information, but at the level of detail that we have with Herschel toward nearby molecular clouds already. This is for nearby molecular clouds, this means probing physical scales of 10 to the minus 2, 10 to the minus 3 parsecs. So really getting down to resolving core scales within molecular clouds, while also being able to make large area maps that start at sort of the diffuse outskirts of these molecular clouds. And if a science question you want to tackle is, how is it that material comes together, forms these molecular clouds, and then fragments or evolves to eventually form these cores and eventually stars? You really need that full range of scales. You really need that high dynamic range information that lets you probe the influence of magnetic fields on the cloud scale, and then all the way down to what's happening in detail within the molecular cloud. And I was struck actually by the estimate in this particular chapter of the science book that you could do essentially the Herschel Gold Belt survey in polarization in about 600 hours in their estimate. Whether that's the exact thing that's done or not remains to be seen, but there is a really, really rich opportunity space here. And so it's time to start really thinking about this, thinking about what we would do with these data. Are we ready to take advantage of them? What are the questions that we need to be working on right now? What's the sort of precursor science that we should be undertaking as a community to make sure that we're ready to take full advantage? That's where I want to talk a little bit today. From my perspective, there's a lot going on in this area in general. I think my own work is gravitating toward using Planck to measure aspects of the magnetic field in the diffuse interstellar medium. And in particular today, I want to highlight some work that we have been doing and want to sort of help the community do using SOFIA HAWC+ data for particular star forming regions. And so the state of play as I see it right now is, we have these beautiful all sky maps of polarized dust emission at relatively low frequency and at relatively large angular scales with Planck. And then we have small maps that were made with individual instruments, in particular the HAWC+ instrument on board SOFIA in the far infrared, probing just pieces of molecular clouds. So PRIMA would really get us the scales in between and far more sensitive and intricate detail on the inner parts of molecular clouds as well. And so one of the things that I want to be your biggest takeaway from the discussion today is that we have very soon for you a new compilation of archival SOFIA HAWC+ data toward a whole bunch of nearby star forming regions. This is work led by my grad student, Kaylin Karpovich, who is fantastic, and who has done some really wonderful work going through the whole SOFIA HAWC+ archive and finding all of the data towards star forming regions and doing the work to re-reduce the data where necessary, to put all of the observations on sort of comparable footing such that one can undertake statistical studies of these observations using this as a set, using this as a reasonably homogeneous set of maps. And so she ended up with 26 star forming regions, many observed in multiple of HAWC+'s 4 bands. And so this is just one map per region to give you a sense of the types of of regions that we are looking at, but then there's much more data than is illustrated just here, and this is already pretty impressive. And so these observations were taken for a number of different reasons, or targeting a number of different types of objects. But broadly speaking, they're all observations of regions of nearby or somewhat nearby star-forming molecular clouds. And you can see that there's really intricate data visualized here in the polarization angle, or in the magnetic field orientation, that we're able to measure with these data. And so some of the maps in this compilation have been analyzed and published before by other authors. So just to highlight a few in particular, here's OMC1 with Chess et al. And M17, one of 3 regions analyzed in this very nice recent paper by Cox et al. And I'm just going to flash this. There are many other authors, and you'll find the full attribution of who took what data and where in particular maps have been published in some form already in the literature, all in a nice table in Caitlin's forthcoming paper. But it's worth emphasizing also that some of these data are not published yet. And this will be the first analysis to use these archival data. So there's just a lot to dig into here. And we're excited both for the analysis that Caitlin has done, and also to get this as a compilation into the hands of others, to start digging into these data, hopefully. This is showing you where these regions lie in projection with respect to the projected map of dust emission in our galaxy. And so you can see, many are in or quite near the plane. Some of the regions are quite close to one another. Many of the regions are observed in multiple bands. And Caitlin has done a really nice job already of analyzing some of the statistical trends in the polarization properties of these data. So in particular, she's looked at the polarization fraction at this S parameter that we discussed briefly before, that is the dispersion of the plane of sky polarization angle. And then she also did the work to fit column density temperature maps using the SOFIA data in combination with Herschel data in order to analyze those properties of these regions as well. This is a lovely visualization. Caitlin has in addition to a talent for the analysis, a talent for visualizing it, which is really a gift. And so this is showing you in a few regions the orientation of the magnetic field in these line segments, and then color coded by this dispersion parameter. And so you can see that the places that your eye would pick up that the magnetic field orientation is very tangled on the scale of this blue circle, which is the beam within which this dispersion is calculated. You can see that that is where this S parameter is higher in units of degrees. So that gives you some sense for how this particular statistic works. Another really nice aspect of this compilation is that we've taken advantage of the fact that our ability to know where these clouds are has really improved in recent years. Most prominently through the fact that Gaia has given us precise distances to many stars that let us precisely locate some of these molecular clouds, or even sub-regions of these molecular clouds in distance. This is showing you a sort of top-down view of the nearby Milky Way with particular molecular clouds labeled at the location that they have been found to lie in distance from, with the use of these techniques for mapping the dust distribution in 3 dimensions. And so Caitlin has used this to great effect because it has allowed us to study the properties of these regions as a function of their distance. And so, for example, here, this is just some statistics on the polarization fraction of the data at each of these different HAWC+ bands. But these are stacked histograms as a function of distance. And so you can see one thing that jumped out of this here, I hope by eye, which is that the polarization fraction sort of skews higher toward more nearby molecular clouds, in particular at these short wavelengths in these band A and band C data, the 53 and 89 micron data in HAWC+. And more than just analyzing these data as a function of distance to the cloud, we wanted to do some of the statistical analysis of these data at common physical resolutions. So we in much of this paper that will come out from Caitlin quite soon, we do our analysis in sort of 2 ways. We analyze common angular resolution, which is of course, a useful thing and what we often do in the study of multi-band polarimetric data. And then we also analyze these data at common physical resolutions using the distances to each of these clouds. And so to do that effectively without losing way too much information by smoothing too much, Caitlin identified a close regime, a sort of bucket of clouds that were more nearby, and then a farther regime of more distant clouds, and shows a common physical resolution for each bucket. So the top panel here, the teal color, is analyzing clouds at a common physical resolution of 0.05 parsecs, and then the far regime 0.3 parsecs. So look for that in this paper. There's a lot of very beautiful analysis, and that's something enabled by having this sort of statistical compilation. Okay, some of these regions that we analyze have coverage in all 4 bands of HAWC+. These ones here in this nice image from the forthcoming paper, but that's not always the case. And one thing that we were keen to analyze with these data, and that will be a real area of discovery and interrogation with PRIMA, is in measuring and understanding what we call the far infrared polarization spectrum. So in other words, the degree of polarization as a function of wavelength in our data. As you can imagine, this requires far infrared polarization at in multiple bands at multiple wavelengths, and this has been done through the years. So I have here a paper from 1999 and a paper from 2025 doing this with various polarimeters throughout the years, where there's a lot of information that should be encoded in this far infrared polarization spectrum that can be difficult to disentangle, because the evolution of the polarization fraction with wavelength can depend in general on the properties of the dust, the composition of the dust, and how the dust grains might be aligned in different populations of dust or dust temperatures that might coexist along the line of sight in your data, in different properties or orientations of the magnetic field that might exist within your beam or along the line of sight in your data that might affect how highly polarized a particular region is or not. These things are interacting in general, or could be interacting in general, to cause an evolution of your polarization spectrum. And so there have been analyses that look at how the polarization spectrum differs, for example, toward dense cloud cores versus in the envelopes of molecular clouds, how this might be affected by the dust temperature or dust column density, and so forth. Caitlin, in this paper that will take the first look at this compilation of HAWC+ data as a whole, did something that I think is quite clever, because we don't always have every region of our clouds covered in every band of HAWC+ data. One thing that you can do to control for differences in column density that might otherwise affect your inference of the polarization spectrum is take the column density distribution at your most limiting band, which in our case is the HAWC+ band A, and then force the column densities of the sight lines that you choose from your other bands to respect that same histogram. So basically sample your data, subsample your data, such that you homogenize the distribution of column densities that you're observing. And so there's a very nice analysis doing precisely that in Caitlin's forthcoming paper, where one of the other things that we are able to say is that we seem to see a stronger dependence of this polarization spectrum, or polarization fraction, on the column density than on the dust temperature. And so at least in these regions, controlling for the column density like that makes a lot of sense. Another open question that we have in the study of galactic magnetic fields is how the galaxy scale magnetic field might be related to the magnetic field in individual molecular clouds that we're interested in probing. And so this is another snapshot from the PRIMA General Observer Science book. This is the Williams et al. Chapter, showing data observed from Enrique Lopez Rodriguez on the scale of a small scale magnetic field within a single giant molecular cloud. This is another place where PRIMA will really shine with its ability to map cloud scale magnetic fields in nearby galaxies and over the entirety of nearby galaxies. As a step toward that, we can look in our compilation whether on these small scales within giant molecular clouds, whether we see any hint that the magnetic field is in general aligned with the galactic plane, because here, of course, we're looking from inside the galaxy and observing things in projection. And we don't seem to see that on the scales that we're sensitive to here across this compilation, which is interesting. This would be consistent with the idea that on these scales, the magnetic field within the molecular cloud has decoupled from whatever large scale field might be out there. And this is something that wouldn't be so interesting to say about one individual observation here, but taking these data as a whole start to have more statistical weight behind it. And so there is much more to say about the beautiful analysis Caitlin has done in this paper. I'm really only scratching the surface here, and I hope you will read it. And most importantly, we're providing this as sort of a homogenized set of data that we hope the community will dig their hands into as something very valuable for PRIMA precursor work and in general. And then I want to say just a few more things about where I see exciting recent developments in our understanding of interstellar magnetic fields. and sort of raise some questions about how we can best prepare ourselves for the PRIMA era. So one thing that is dramatically improved in recent years, although it's been decades-long work in progress for the community, is to understand the three-dimensional distribution of dust in the nearby ISM. So this is showing you the nearest few kiloparsecs around the sun. The sun is in the center of the volume here, mapped using reddening toward many stars, and the very precise distances toward those stars afforded to us by Gaia, and then some clever technical work to turn those observations into this three-dimensional map. That's opened up a lot of new questions that we can ask about the ISM that we couldn't before when we saw everything in projection or as an integral along the line of sight. In dust polarization, we've been able to use the combination of these 3D dust maps and Planck data to at least statistically detect the effect of the three-dimensional tangling of magnetic fields along the line of sight on depolarization of the dust polarization fraction. So this is work led by my former grad student George Halal and along with Manish Tahani, comparing sightlines that in the 3D dust distribution had relatively simple distribution of the dust along the line of sight to comparable column density sightlines where the dust was more complicated in its distribution along the line of sight. And you can set up your experiment that way and make a measurement of the degree of depolarization that you get from just the geometric depolarization of having dust distributed more spread out along the line of sight, and therefore sitting statistically in more differently oriented magnetic fields, contributing to that geometric depolarization. Another beautiful piece of work along this line of exploring that third dimension is Gina Panopoulou's work using starlight polarization. So starlight polarization is a more direct handle on what's happening in that third dimension because you have the distance to the star. But it still takes some work to go from these starlight polarization measurements to an inference of the magnetic field orientation as a function of distance along the line of sight. And we should be thinking about this not because you can directly measure that from dust polarization, but because measurements of far infrared dust polarization, I think, have a lot to contribute to this sort of analysis in our understanding of the dust that's giving rise to the polarization, in measurements that in multiband data are or could be sensitive to different populations of dust along the line of sight, and so forth. And so when we think about we should think about this not just as exciting developments in our field, but also like how can we really push the envelope of combining starlight polarization and polarized dust emission to do this even better. One other set of ancillary data that we need to grapple with how to combine are these Zeeman measurements that I mentioned give us the best probe of the magnetic field strength in the neutral and or molecular ISM. And so my grad student Marta Nowatka has done beautiful work with archival H1 Zeeman absorption polarization data. Here she's taking these measurements where you have a measurement of the magnetic field strength in a particular absorber towards some background source, and she's looking at closely separated pairs of sources on the sky as a function of where the absorber is in velocity space. And what she found is that at coincident velocities, the measurement of the magnetic field strength tended to be, or really actually was, to very good precision, the same magnetic field strength in closely spaced absorbers out to a separation of a few degrees or so. And Marta then noticed something very interesting, comparing the number of those absorption components to the number of peaks in the 3D dust distribution, which is that those two things tend to be quite correlated, which means that you can assign at least a lower limit on a physical scale for the scale at which you're measuring a magnetic field strength that is the same within your error bars in these data. And so that lets us say that in this cold H1 where these Zeeman measurements are making, the magnetic field seems to be approximately coherent on scales of approximately 7 parsecs or so. And so this, I think, is well, it's an intriguing result on its own, and then we should think about how this fits into the bigger picture of the evolution of field strength with density in the interstellar medium. And finally, I'm just going to flash that a big area of inquiry for me is really to understand how the phase structure of the multi-phase interstellar medium is interplaying with the magnetic field structure of the interstellar magnetic field. And I think we've made some big steps forward there lately, in particular because we can take measurements of our data that let us probe the fraction of a sightline, the mass fraction of a sightline that is in the cold neutral medium in the H1, and compare that to dust polarization measurements. For example, the dust polarization fraction with Planck. So my grad student Minchi Lei found this very nice correlation between the dust polarization fraction and the mass fraction of C&M that we turned into a constraint on the degree of geometric depolarization in the dust associated with the cold neutral medium compared to the dust associated with the warmer gas. So I'm just going to flash that, but I'm excited about it. I'm very happy to talk about it. So I want us to think together really about how do we optimally combine our different tracers of magnetic fields? What can we be doing now to prepare ourselves with ancillary data, including information we have on the 3D distribution of the ISM, to get ready for PRIMA? What theoretical work we still need to do, in particular to understand some of the degeneracies in our far-infrared polarization data that we might care about when we train our eyes on a particular region. And I also want to raise that some of the things that we found from Planck data were basically unexpected. And so, how do we set ourselves up for discovery in the PRIMA era? I will leave you with these as my conclusions, and please look forward to Caitlin's paper coming at you very soon. Thank you.
Great, thank you so much, Susan. So we have time now to take questions from the audience. Great, we have a couple of hands raised. Let's start with Doug.
Hey, Susan, that was excellent as always. Thank you. Just a quick question. What do you think? So we need PRIMA. PRIMA is incredibly important. But what do you think is the most important ground-based facility in support of it? Do you think it's all the way to ALMA, or do you still think we need at those longer wavelengths the higher resolution of something like a CCAT or something even larger like at LAST?
Yeah, I mean, you can't possibly make me choose. I think we need it all. I think these different facilities have different strengths. There is huge benefit in having the lever arm of many different frequencies with sensitive measurements of the polarization. There are some capabilities that are tailored toward targeted observations of small regions, which is, yeah, the ALMA absolutely shines there. But then, you know, I care a lot about understanding the diffuse ISM, the magnetic fields and the dust in those regions, and having these very large area maps with CCAT will be really transformative for that. So it's all the above. I refuse to choose favorites.
Thank you. Spoken like a mom.
Thank you.
Excellent.
Yes.
All right, next up, Darren.
Well, thank you for the talk. I really enjoyed the breadth of work you're doing there and hearing about it. I did especially want to compliment the work on the archival HAWC+ data. I did have a question from that. From looking at a number of regions there, are you finding places where you think the grains are not aligned? And then, you know, conversely, how would one design observations in terms of like wavelength choice or field coverage to avoid such regions with PRIMA?
Ooh, yeah. I mean, this is a great question. I would say we haven't yet done the deep dive on an individual region to try and fully understand. We've been focused at the outset on more general statistical properties of these regions. I'm very curious how we can use, I mean, the sensitivity and the wavelength coverage of PRIMA is already, I think, very well attuned to doing this type of science. And then I'm very curious on how we can best set ourselves up by understanding sort of other properties of the geometry of the regions that we target, other properties of the distribution of the dust and the gas in 3 dimensions, other properties of the radiation field we think are incident on the dust, to really sort of design the ideal experiment. Because I mean, as you know better than anyone, you know, sometimes you approach these data, you make your measurement, and you're just left with this uncertainty of well, it could be an evolution in the alignment of the grains, you know, or we could explain this in one of these multiple other ways. And so, yeah, I mean, I think I'm very curious to think about how we can nail this down and really design hopefully definitive experiments on this question. Caitlin should feel free to hop in if she has better things to say.
All right, we have another question from Gina.
Yeah, hi, Susan. Good to hear about all these results. So I was curious about the result you mentioned on whether the mean field of the clouds and the HAWC+ data, whether it connects to the large scale field. And this result you showed, it reminded me of one similar work by Ian Stevens back in 2010, finding the same decorrelation. But then I think about Dan Clemens' survey in the near infrared, where he finds that the magnetic field is not in the plane of the galaxy. If you look at, you know, the distance separated stellar polarizations. So I'm wondering, the fact that you find the magnetic field of the molecular cloud not parallel to the galactic plane, that doesn't necessarily mean that it's not connected to the local large scale field, right?
Yes, that's a really good point. Yeah, fantastic. Yeah, I agree.
Okay, there's still an open question there, but right.
There's definitely still an open question there. Yeah.
Thanks.
Thank you.
All right, any last questions? If not, then I'd like to thank Susan one last time for a really excellent talk, and I hope to see folks next month. And this talk, like all of our others, will be posted on YouTube. So if someone you know had to miss it, please let them know that they can find it there. All right, take care, everyone.
Thank you so much.